Hey everybody, the purpose of this video is to review what you were supposed to get out of that series parallel, those two activities that you did through the PhET simulations. So we're going to go through this sort of quick. What I'm going to do is I'm going to make a list of everything series, everything parallel that's important that will be applied to future problem solving. So first we're going to start with series. And we'll just kind of go through the activities. I'm doing this from memory because I don't have them in front of me. But I'm pretty sure in the first activity, when you added a second light bulb, they both got dimmer. This would imply that the amount of current flowing through the circuit became less and that the amount of resistance was increasing. So the concept you're supposed to get out of that is that adding resistors in series makes the total resistance go up and the total current decreases. So adding resistors in series makes the total resistance go up. Now, total resistance is going to be known as REQ, equivalent resistance. Resistance, I can't spell as usual. Resistance, again, that's going to be REQ for equivalent. Increase. So the total current flowing in the circuit will decrease. Total current decreases. And obviously vice versa. So no need to say it, but it's obviously true. Also, from that first of the two activities you've just seen, when one goes out, they all go out. Not they all, but anything in series with it does. One goes out, all go out. I mean, you're literally cutting the circuit. So if this was your light bulb, there is now a hole and the current can't jump that gap. It's just not possible. As you moved on through the activities and you got to the second one, you should have seen that in series, the one with more resistance was the brighter one. So, sorry, spaced out for a second. Power is directly related to resistance when it comes to series. Power is directly related to resistance. The one that had more resistance should have been brighter. Then, when you got to the second activity, which is a little bit more math-based, probably the most important concept here. I'll even start in a different color. Now it's special. In series, this is the most important thing because it dictates everything. The current is the same everywhere. That's super important. Anything in series, they have the same current. You can't have one electron flow through a resistor and then disappear. That electron then has to go through everything else. You can't lose current. So everybody gets the same current. Also, you should have seen that, I like that purple, I like this one better, that the total resistance, the R equivalent in series, is simply the sum of the resistor values, however many there are, and that the voltage total was the sum of the voltages, V1 plus V2 plus V3, however many there are. So now, back to the power is the same everywhere. The current is the same everywhere, and power is directly related to resistance. Just want to highlight this for you. I tend to use P equals I squared R. You don't have to, but if the current's the same everywhere, then you could see that power and resistance have a direct relationship. So I tend to use P equals I squared R for series, but that's not always the case. That's everything you should have seen with the resistors in series. Then there is parallel. So in parallel, when you added another light bulb, it was just as bright as the first one. That means each of them is getting the same amount of current, which means the voltage source has to supply even more current. Therefore, if you're supplying more current, the resistance must be going down. So for this one, adding resistors makes the total resistance decrease, and therefore the total current will increase. Total current increases. Then if you removed one of the bulbs, the other one stayed on. One goes out, others stay on. So, I mean, basically, when one goes out, you have your little circuit here with a light bulb, and then you have another one and a light bulb here. If you remove this one on the right here, it doesn't matter. The current can still flow through that resistor there. And as you moved on through the activity, you should have seen that the one with less resistance was more powerful. So in this case, power is inversely proportional, like legitimately inversely related or proportional to resistance, which should hopefully make sense. You have two clogged paths, one with a 10, one with a 50 ohm resistor. If it was a clog in a pipe, the water would go through the pipe that has less flow. So the one with less resistance is going to get more current and therefore create more power. Now, probably the most important thing with parallel, and we'll make it a pretty red color. In case you didn't notice it, the voltage is the same everywhere. That's very important. Voltage, same everywhere. So there's that. And then you were given the resistor equations. So that one, to find the total resistance, R equivalent is just 1 over R1 plus 1 over R2 plus 1 over R3, however many there are. And then the last thing you were to get out of that was that the current going into a junction, or the total current in this case, but the current going into a junction, you may hear me say in the future, is simply the sum of the currents. And that's it. Now, again, with the power, if we go back to that the voltage is the same everywhere, and we look at the equation P equals V squared over R, where that's the same for all, you can see that inverse relationship between resistance and power. So that's basically it when it comes to the important concepts for series and parallel. I would take this and put it in your notes and just have it out as you start to do homework, because you'll refer to it to answer questions, and then eventually you'll just know these things without thinking about them. So any questions, do not hesitate to send me an email, and thanks for your time.